First, huge thanks for having me. It's really awesome to have the opportunity to like remotely meet some of the rest of the community. I'm calling in from Berlin, so not too far away. And this is a talk I've been kind of working on. It's like a collection of thoughts around garbage collection and Go, and trying to think of a clever name. I came up with this garbage diving for Gophers, which, if no one's familiar with this term, it's predominantly called dumpster diving, and it's like when you go in to a garbage truck and then like try to see if you can pick out some good bits. So my talk is a play on that, and it's really about kind of digging into what is going on in garbage collection in Go. So what's this talk trying to deliver? Well, I'd like to start by also saying this is hopefully a somewhat beginner-friendly talk as well. I'm trying to hit all levels. So I want to give like a general overview of what garbage collection is, why we have it in Go, the main mechanics, looking at it more at a behavioral aspect rather than implementation. So looking into like how it's working, and when it's happening in our programs. Then I'd like to look a little bit at tooling, because Go gives us some awesome tooling to be able to inspect and look at how our program is behaving. And there's a lot also around the garbage collection, which if you're not familiar with, is something really exciting to explore. And then maybe a few ideas around techniques that you might be able to apply to make your code run a little bit more sympathetic for the garbage collection. So how we as developers can have like an impact on this process within our programs. So it's very much a work in progress, as I mentioned before, and I'm very open to feedback. Please be kind. But yeah, if you have any ideas, things that I might have missed, I'm really open to hearing back from you, either through Slack, as Vatek mentioned, or through the chat. I won't be looking at the chat during this presentation, but I'll have a look afterwards. Okay, so yeah, who am I and why am I speaking to you today? So my name's Jessica. I'm a backend software engineer at Ecosia, which is a search engine that plants trees. You'll find me almost everywhere under the handle @SleepyPioneer. I am a career changer. I switched into tech in 2018, coming from one career in the film industry as a camera assistant and another career as a specialty coffee roaster. So a bit of a diverse background, and found my way into tech and kind of really dug into Go. I'm an avid community member. I really love being involved in the community, and I always consider myself self-taught, but also very importantly, community taught. And I'm also an active member in the Go group in Berlin, but also Women Who Go Berlin. So what is garbage collection and why would we need it in the first place? Well, memory is not endless, and it's going to have to be released at some point. So the way that we are typically writing code is to assign values to memory so we can use them at a later point. But at some point, they're no longer in use, and we no longer need these values. So what's going to happen to them? And if you think of it as a pile that we just keep throwing things on, at some point, that's going to take up the entire space, the entire memory of our program. So it's really important to think about actually where these allocations or like where these stored values are going. And we kind of have these two places that we can consider of like the heap and the stack. And I think what's important to remember in Go is that when we have, it's quite a complex memory management. When we have multiple Go routines, they all have their own stacks, and stacks are lasting for a period of time for a particular function. But anything that's escaping out of that and going onto the heap is going to persist for longer. And at some point, that is what we're going to have to reclaim. So garbage collection is predominantly looking at what's on the heap, what's being pointed to, what's in use. And if it's not, then can we remove it? And the big risk here would be running out of memory, and then our program would completely stop to function. So it's realistic problem. I mean, I think we live in an era where we have a lot of resources, depending on what kind of work you're doing. But at some point, that is the risk that you're going to run into. So how would you know whether a variable is going onto the heap or the stack? Well, with Go, actually, according to their docs, you don't really need to know. Like the compiler is doing a lot of things to like accommodate this for you. So as a developer, actually, you maybe don't have to be as concerned as you would with a different language to where your allocations are ending up. But of course, the caveat here is we want to have a look at that because that's going to be the main player into understanding how and when our garbage collector is running. So how would we clean up allocations? Well, I've already mentioned the garbage collector, but imagine that was not an option at the moment. Well, we would have to actually go in as developers and manually write code for that would check if values were in use, check if there's a reference to a value, and maybe do some sort of mark. There's different algorithms for this, of course, but essentially find out if it was in use or not, and if it was not in use, then write some code to like clean it up. Of course, in a better option for us developers would be if there was some sort of built-in operation to check those values and clean them up when they're no longer needed, i.e. garbage collector. So let's talk about Go's garbage collector. Now we've kind of got a little bit of an understanding of why we would need a garbage collection in the first place and what it's actually going to achieve for us. Well, while there's other languages approaching this in many different ways, I think what's really interesting about Go's garbage collection is since 1.5, they went for this concurrent collection pattern. And they were really looking to have low latency within the garbage collection so that programs were not stopped or prevented from running by garbage collection, or at least for the least amount of time possible. Of course, that's also going to come out with its own trade-offs. But I think it's like a very conscious decision by the Go team. I'm going to dig a little bit into the benefits of that. So I think when we are working predominantly as Go software normally is work like running on the cloud, we do have to think of the fact that the resources are essentially equaling dollars, they're equaling money. If you're going to pile up memory, you're going to need another instance, or you're going to have to like start to scale your program to a certain extent. So it makes sense to keep it lean for cost reasons, which is why it's also a necessity to have garbage collection. And also, as I mentioned before, the memory management in Golang is fairly complicated because we have a lot of concurrency. Like everything in Go is and when you start to learn Golang, I think it's one of the first things you start to hear about is that Go is concurrent, it's built for concurrency, and each Go routine having a different stack is then a lot of things to try and manage at once. And to try and do that manually, I think would be not impossible, but fairly difficult. So I think, the Go team thought this is really a must for a modern language. And they really felt like it was very important for Go to do it in a way that would reduce the amount of causes that were necessary for this process to happen. And really have something that would fit into the language the way that the language is running in other ways. So with concurrency in mind. So I think if you look back through the history of Go a little bit, in Go 1.5, they made this statement of that we're going to build a garbage collector not only for 2015 when they were finally getting to the point of releasing and developing this, but also for 2025 and beyond. So they were looking forwards and saying, what use are our programs, or what use are programs written in Go going to have? Where are they going to run? And then what makes the most sense for a garbage collector to live in that environment? So again, as I've mentioned already, low latency. and ensuring that the programs would be paused for the smallest amount of time possible was very important. They also decided to, interestingly, actually use an algorithm which was like fairly old. It was from like 1978, the Distra algorithm, and it's this tricolor mark sweep collector concept, which I will go over a little bit as well. I think that's quite interesting. Like, you look at languages like Java, and they have many different algorithms you can implement. But with Go, and I think overall with Go, one of the really awesome things, or at least one of the things I love about the language, is that they tend to lean towards simplicity, and it can be maybe also described as opinionated, but it keeps things to a point where I think it makes it very accessible if you're learning, and it also kind of guides you in a way of saying, like, this is the Go way of doing things. So let's talk a little bit now about how garbage collection actually is happening. So split it into three main parts here. So we have a pacer that's running in the background. And this pacer is going to determine the length of the collections and like when they're going to happen. And its main job is to ensure that garbage collection finishes before we run out of memory. So this makes a lot of sense. If our program runs out of memory and then we say, oh, maybe we should do garbage collection now, we're probably going to hit issues. So it has like a feedback loop to ensure that this is going to happen just before that point or before that point. Then we have also marking. So this is what I mentioned about it having a mark sweep process. So we're inspecting values, we're looking to see if they're referenced from somewhere else and marking them as in use, which of course would leave us with values that are not marked at all, and they're the ones that we're ready to clean up. And that's where we come to the third stage of sweeping, where we can actually clean up the unused values. So let's talk a little bit about the pacer. How does it even know when to start garbage collection? Well, as I hinted at, it relies on a feedback loop to be able to gather information about how the application is actually running. And just before each collection, it can calculate an estimation of the amount of time to complete the collection. After the collection's run, it's going to look at what memory is still in use, and then it's going to make a decision based on the single control that we have over the garbage collector, which is called the garbage collector percentage. And we'll touch a little bit more on that in a little bit. Its default value is 100. So assuming for now that it's just at its default, it's going to set the upper limit for the memory. So essentially, it's going to say, just before I reach this memory point, that's when you need to run garbage collection. So let's look a little bit tighter at that. So imagine the garbage collector runs. The first time it runs, it's cleaned out anything that is not in use, but it finds that there's 2 megabytes in use. Just as an example, I mean, this is overly simplifying actually what's going on here, but hopefully this is just to make it clearer of the kind of behavior that we're seeing. So assuming that the garbage collector percentage is set to 100, which as mentioned is the default, then the heap is going to be doubled. So that means that it will wait until it's 4 megabytes or just before 4 megabytes before it runs garbage collection again. This is continuous. So imagine the next time it runs and it finishes with 5 megabytes in use. Well, then the pacer is going to assign another 5 megabytes on top. So the next collection after that will run at or just before the 10 megabytes mark. So this feedback loop really allows it to be dynamic and allows it to scale and actually be sympathetic to the program and what the program's needs are. So let's have a look at the marking step of the garbage collection. There's 2 points within this where we're going to have stop the world time. This is time when no other processes can actually be running. And as I alluded to, this was for the Go team what they wanted to make absolute minimal, and they've worked on bringing the time down to like incredibly short amount of stop the world time. But it's important to remember that it's there, and it's necessary because we need to be able to turn the right barrier on during this point to ensure that while we're doing our marking, we're not suddenly changing our references and going to then end up missing or removing something that we actually later need. So all application Go routines are going to have to be stopped. And you'll also see this called sweep termination, where it ensures that all sweeping from the previous round has been completed. Next step is going to be the inspection and the marking, and that's going to be able to happen concurrently. So it's going to transfer along all the memory points, looking to see where the different references go to. So it will start on everything that's on the stack, and then it will look to what values are then pointing over to the heap, and it will like follow them along to check, to make sure essentially that it has checked all values to see if they are in use or being referenced. Going to mark those in use, and then of course any that are not marked are the ones that are ready for collection. And that brings us then to mark termination. We need to turn the write barrier off, and this is again stop the world time. So again, this is a small pause in our program, and this is the point where the pacer can calculate the next collection. So what we've just talked about of it having a look to see what's been collected in this last round, what memory is actually in use, and make that calculation for when it's going to run again. So let's swap gears a little bit and look specifically at this concurrent section of the inspection and marking. So in this example, we've got 4 Go routines, again, very simplified. And at the start, they're going to be running application work until we go into the stop the world time. Then they're going to have to stop. And first, we're going to have to wait for them to stop so that we can turn the write barrier on. And once the write barrier is turned on and the stop the world time ends, roughly about 25% of our CPU, so one of these process threads, is going to be used for garbage collection. In this example, that's 1 Go routine. However, that may not be enough, and there can be times when marking is taking too long, and the application is going to risk that the heap memory is going to reach its limit and potentially end up with the program crashing. So in this scenario, the other Go routines will also be assigned some marking work, and this is called mark assist. And in this example, that will then mean like 2 of the Go routines, like 50% of our CPU, is then going to be used for garbage collection. And the amount of time that the Go routine will be assigned to mark assist is going to be proportional to the amount of memory that's that has to be done. Then we enter our second stop the world phase, mark termination, as we talked about before. Everything has to stop again. And sorry, just in case it wasn't clear on this slide, the other Go routines are still doing program work. So we can still continue to have our application run. This is happening in concurrency. And it's only these 2 sections where we have stop the world time where we actually have to stop doing program work. And after that, all of our Go routines can go back to program work. So the last step in that would be the sweeping. And what I think is quite interesting is that that actually just happens when Go routines are trying to allocate new values to the heap. So the cost of sweeping is actually not part of the cost of garbage collection. It rather is an added cost to later allocations. I think this is helpful to bear in mind, because you don't have to think about that during the garbage collection happening, but you do need to think that there's this going on when you're making further allocations in your program. So let's see this a little bit in action. I can share all the slides with you as well, and including this link to the repo. But I wanted to make a little bit of let me just get out of this. A little bit of a code example, because I don't know about everyone in this group, but for me, like, a visual aid really helps me grasp what's going on. And yeah, when we're talking about code, doing something with code definitely helps. This repo has a small README. It's not really meant to be an individual learning resource. I don't think it's documented well enough for that. But I tried to apply README, so if you are looking at it later in your own time, you're able to read through a little bit what the ideas were behind this. So essentially here I have a program that is repeating a function X amount of times. And this function actually is making a rather larger, so medium-sized allocation and printing the length. So nothing overly complicated, just something more to demonstrate when allocations are actually being made. And I think the first thing we want to check here is if this is actually staying on the stack or if this is actually going out to the heap. So one of the first commands we can use is this gc flags command with the -m. This is going to give us an output that will show us if we are indeed escaping to the heap or if it's staying or if it does not escape. So if we check the lines here, and I hope this is large enough on the Zoom screen for everybody. Yeah, perfect. Thank you. You can see here that, yes, indeed, this is escaping to the heap. In fact, actually, also this length function is also escaping out as well. So in our case, that's good because we want to be able to observe the garbage collector. What we're going to add next is tracing. So I've added this in a second package in here, just to keep the main package clean, a little bit more clean. Let me just make this a little bit larger for you all. This is essentially taking the example from the docs. So I've learned a lot in programming. It's good to check the docs. And this is their example. So essentially all this is going to add is it's going to run our program from main.go, but add tracing to it. So I will just swap around which one is running. I'm aware I didn't start a timer, Vortex, so could you give me some indication for when I start to get out of time?
I will.
I want to be respectful to the other speakers. And yeah, let's now run this command. And I've altered the command slightly. I will explain why. So I've altered the command slightly to ensure that it will run on one processing thread. That's just because then it's easier to look at when we go to the tracing tool. And what I've put on here is I've put on the garbage collecting tracer, which will give us an output so we can have a look to see when the garbage collector is actually running and what kind of things it's looking for. So what we see in this output is, like, first of all, a little overwhelming of different numbers, but it is actually quite interesting information. And there's a key that's in the documents I've also included in the README that allows us to see what it's referring to. So the first number is which garbage collection it is. So we have one collection, then a second collection, then a third collection. But what's interesting for us to look at is to see the different goals that it has. And that's really tying back into the diagram that I showed you of when the pacer is looking to see what's in use after it's done the collection and then reassigning. And at this point, we can see don't forget also this is set on a default, so that garbage collection percentage is 100. We can see that it is pretty consistent, which is a good sign for us because it means that garbage collection is running regularly and that it's able to keep up with the amount of allocations happening. Which again, we wouldn't really expect it to be different because our program in this case is not actually doing too much. I think I will skip that. So the next thing we're going to look at is the actual trace output itself, because as I mentioned, for me, I'm very like visual person. So being able to look at these outputs really helps me understand better what's going on. And I think it's so wonderful that we have these tools in Go to be able to analyze our code and analyze our programs. And even if you're just starting out, I've been programming for a couple of years now, so not too long. And I think this gives you a great insight of understanding a little better what effect your code can have on how the program itself is running. And there's two things I'd like to point out here. First of all, I'd like to point out the heap that we see along this line. And we can see it's indeed going up and then going down as garbage collection is happening. We can see various stages of garbage collection being marked down on this bottom in the one process thread that we have. So ideally on this tool, you need to zoom in a little bit. Oh, sorry, wrong one. To actually be able to read what's going on here. So the GC or garbage collection line across the top will tell you the actual points where garbage collection is happening. But then you can also dig into the lower down parts, to see what part of garbage collection is actually happening. I should have. Maybe played around a little bit beforehand. The mark assist you can see very well, but I wanted to try to find the one that is running, the other parts of the collection. So here down the bottom, it's giving you an indication of actually what's going on and more information of when it's starting, when it's stopping. This is also similar to what we saw in the command line output, but I think it's a lot more understandable from here. And what I would encourage everyone then to do is to play with this a little bit and also to experiment a little bit with this one kind of control that we currently have, which is this Go GC control. And you can just turn it up, turn it down. It's part of the Go debug variable. You can see the command here. And I think it's quite interesting to see the effect. I'm going to switch back to my slides quickly because I have more that I wanted to present. But as I mentioned, I will share the GitHub with you all, and then you can try run that also yourselves. And maybe then also for people who are a bit new to these tools, they can also see how to implement them in their own programs. So the point I'm trying to make here is that a careful, well, in my opinion, informed programmer can actually reduce the garbage collection overhead and quite dramatically if you're using the language well. And that's actually a quote from the Golang docs themselves. So they also seem to think so. And that's what I'd like to talk a little bit more on to wrap up. So yes, as mentioned, the Go trace tool is the tool that I was just showing you. And it's fairly well documented to get started with. And in this screenshot that I took yesterday, you can see a lot better the different stages of garbage collection. So you can see here the sweep happening, here's the sweep termination happening, and then the mark assist. So yeah, how do we optimize for garbage collection? And seemingly when we have endless amount of resources and maybe don't need to think as much about our memory allocations, how can we develop a sympathy for the machines our programs are running on? Well, I'd like to share with you these three ideas. And I'd be very happy to discuss these more, maybe in the chat session. But I think the first thing you can start to think about is how can you reduce the number of values that are going on the heap in the first place? So how can we be a little more mindful of when we allocate? And I think the first thing is awareness. So for me, when I was learning about this, it was like very exciting actually to learn about how the code I write actually has quite a big impact on the underlying hardware. How can we reduce the amount of allocated memory? So do we need to save maybe the whole thing, or can we make allocations that are a bit smaller and be a little bit more precise with the values that we actually want to keep persistent and be able to keep around in the program? And maybe also reducing the number of Go routines allocating in the first place. So like less complex memory management is also going to help our garbage collector be able to be more efficient. So of course, it's exciting when you learn about Go routines and you want to add them into everything. For sure, I did this. But maybe it's not as necessary as one would hope. Yeah. And the future of Go's GC, do I think is going to change drastically? I mean, definitely compared to other languages. I think it's interesting that we only have this one control knob, this GC percentage. I've read through at this weekend a lot of the proposals in the Golang GitHub repo, and maybe there's some people even from the Go team joining this evening that can comment more. But it seems to me like keeping it simple is the intention. There's talk around being able to set a maximum heap value, which would then give you a little bit more like that would have a knock-on effect to then how much memory you would be able to allocate and how often your garbage collector would need to run. But it certainly looks for the time being that the approach is going to be more that we need to think about our memory management and be careful as Go developers, but also be aware about when garbage collection is happening. So just to sum it up, what I've covered is a little bit around what is garbage collection and why we need it. So hopefully you're not leaving today thinking, I have no idea what garbage collection is. Also, a little bit around Golang's garbage collection specifically and why it's been included in the language. The different phases of garbage collection. Stop the world time and the latency, like this is the cost of having garbage collection in the first place. And also shared a few ideas of how you could optimize your code or how to think a little bit more sympathetically towards the garbage collector itself. Obviously, I haven't included everything. In fact, there's many aspects of this topic. It's really exciting one to jump into. And I think one of the big things to remember that this talk is not touching on a lot of the edge cases. And that's something that I would like to spend more time looking into myself. The other thing is I think it'd be really interesting to look a little bit more into the different types of algorithms, because as I mentioned earlier in the talk, Go has chosen this one specific algorithm to kind of work with and optimize on top of, but there are other ones out there. So a few credits. Big thanks to Daria, who is one of the fellow Women Who Go Berlin members. She collaborated. Actually, this entire material is supposed to be part of a book for GoBridge that kind of has been put on pause. But that's why I wanted to, take advantage of having done the time and put in the work to research this topic to maybe create a talk. Big thanks to Bill Kennedy, because he's been a very big inspiration and very supportive, and also to Rona, who's one of the Women Who Go organizers in Berlin. This is the resources. Again, I'll share the slides so you can just take them from there. There's some great reading on this topic for sure. I could add to this list. And yeah, thanks for listening.